Swayam Prabha. Digital India. Educated India.
Today, we will start with the basic concept of force, traction, and stress. And then we will build on that gradually the stress analysis, how do you analyze stresses and all this. So the first thing is, I think you know the definition of force. So I'm not going into that. You have studied it in Newton's second law or some other form. Now, what is traction? We start from there. The traction vector is basically a force acting, let's say, this is the area, and some force is acting on this, and so this force divided by the area is what we call traction. So the unit of traction is also Newton per, let's say, millimeter square or meter square, or if you are writing in Pascal, then it is Newton per meter square. Okay, so this is same. Now, can anybody tell me what is pressure? How we define pressure?
Force applied per unit area.
This is same as traction then? Is it the same thing?
So that is perpendicular force.
One at a time. I think you can one at a time. So what is the difference between then pressure and traction?
The pressure, in the case of pressure, the force applied is perpendicular to the area.
Correct. Okay. And mostly pressure is used with fluid. We normally, when we say, let's say, gas pressure or a liquid pressure, it's not traction we call. Okay. Because I will tell you later, traction is also associated with shearing, and pressure doesn't give shearing. Pressure is only normal to the plane. But the unit is same. Okay. It is the same unit. Okay. Same as the stress. The unit is also this. But all three are different. The traction, pressure, and stress, these three are different terminologies, and they have different connotation and meaning altogether. So the traction is, it doesn't matter whether it is perpendicular or not to the surface. The total force acting on that surface, or the net force acting on that surface, divided by the area. Okay, that is what we call traction. So if I now know the traction, what is stress? What is this? Mostly we have two types of stresses. One is called normal stress, which is perpendicular to a surface, and another is shear stress, which basically acts along the surface. Now, in a 2D format, what I have shown here, in surface will become a line, and it is probably acting along this line, either in this direction, or in it may be in this direction, or it may be in that direction. Okay. In 2D, it may be like that. That is what is the shearing, or the shear stress or shear force. And normal will be the perpendicular to this. Okay, I could not draw it, but it is the perpendicular. This will be 90 degree. Okay. Now, if you see in 3D, then in 3D, so there will be, infinite way this shear stress can be, oriented along the plane. Okay. So there is n number or infinite way we can do it. But we normally define then the two perpendicular axes, and we take those two directions. Now, how does this traction, which is T, relate to the stress, which is the normal stress sigma? Later on, we'll write it as a sigma n, and the shear stress tau. Normally, we designate it by tau. So, how they are related to each other? It just then this traction oriented towards the normal direction. So it is the unit normal vector, and this oriented towards the shear direction, which is the unit normal vector in shear direction. So, and you know this dot, meaning the dot product. So it is the oriented in this. Now, in this case, particularly in this case, you see that sigma and tau both are given as a scalar unit, as a scalar. Okay, just the the values we have given. Okay, but do not confuse. Okay, the stress is not a scalar quantity. Stress is even more than a vector quantity. We call it a tensor. Okay, so I will come to that later. So in this format, because it's a I have done a dot product. So dot product returns a scalar value. That's why it is showing just the magnitude part of it. There is no direction, no plane associated with it right now. Okay. So if I know now the traction vector, and traction is a vector, mind that. So it will have a direction, and then if I know any surface whose normal or unit normal vector and the shear unit vector, then we'll be able to at least calculate the magnitude in those two directions of these two important stresses. One is called normal stress, which is normal to the plane, and another is shear stress, which is along the plane. So by definition then, you are saying if this vector n changes, so that the sigma. So you see, T remains as it is, but it will also change. Because of this, you see, this plane is controlling this value. And that's why it is no way basically just a scalar quantity. It's related to the plane. And that's why it is called a tensor quantity. Okay. So right now you remember there is two stresses. One is normal, another is shear. In 2D, there will be one normal, one shear. In 3D, there will be one normal and two shear in two perpendicular direction along the plane. Okay. Now let's do a simple example. Okay, which I guess you will be, and you'll be able to do. Let's say force 5000 IN is acting, and it's applied on an area of, let's say in this area, which is 200 millimeter square. Okay. Then I have cut the face in AA dash, which has a 30-degree angle with the vertical. So if I draw a 30-degree, so this is 30-degree angle. Okay. Now you determine the traction along the AA dash plane as well as normal stress and shear stress. Okay. The question is clear to you? A force F acting on a 200 square millimeter area along this, and which is perpendicular to that force. And then I have cut this along this line, which is 30-degree with the vertical. Now the question is, what is the traction vector, the value, or along the AA dash and along the AA dash and as well as along as well as normal and shear stress. Okay. Now, how we can do that? This 200. Just a minute. I'm getting a call. I have to just. Sundar, hello. Okay. So the area will become 200 by cos 30 A dash area. So this is my new area. The force remains the same because this is the force acting on F. So my new traction will be this, and previous traction was 5000 divided by 200 Newton per millimeter square, and now the traction changes to this. Now the unit normal vector along this line will be n will be cos 30i plus sin 30j, s will be minus sin 30i plus cos 30j. I think these two relationships probably you know, or we can also derive that later on. If the angle is 30, then what will be n? This cos 30 and this is sin 30, and this one will be just reverse, minus sin 30 and plus cos 30. Okay, this s direction. See, minus sin 30 plus cos 30. Okay. So the applying that formula what I gave, T dot n. So the T dot n will give me, this is just this. So 18.75 and tau equals to 21.65, which is the new traction in this. So this value we are getting 10 point. So there will be a minus. I think I missed that minus. Okay. You understood this part? How we calculate this, or any confusion? Anybody? Everybody understood? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
That's
Yes,
nice.
yes, sir.
Yes, sir.
Okay, great. Now, yeah, you should not go to sleep. Okay. Now, determine this. I will give the hint later. I'm giving you 2 minutes. It's the same thing. Just I change the direction. Let's say this is a surface. I have drawn the tree very poorly anyway. So certain meter below, the stresses on this line is 5 MPa. And let's say my AA dash line is, now mind that this is the stress, or you can say the traction also, because it's the same thing. In this case, it is the same thing. Or I can say that the normal stress vector along the horizontal plane is 5 MPa. Now this plane has rotated 60-degree clockwise. Okay, 60-degree clockwise, and you have to tell me what will be the traction as well as normal and shear stresses along AA dash line. I give you 2 minutes and tell me the answer. Chamant, you take the time. Okay.
Yes, sir.
मी क्लास आहे मग क्लास आणि आज आपण मिस
traction will be 2.5 MPa.
Sir, could you please unmute yourself, sir?
Yeah.
Sir? Yeah, fine, sir.
Oh, okay. Somehow it got unmuted.
Actually, you were talking on a call now, so I just muted you for some time.
Right? Yeah, okay. I'm still learning this new thing. Okay, somebody said the answer. Let me write it down. A dash is 5. Oh, sorry. Okay. Everybody got how it has come? Well, the minus sign, minus 60 degree, we normally take because if any angle rotating from the horizontal clockwise, we normally take negative value. And if it is counterclockwise, we take positive value. Remember this, okay? Positive angle is when the angle or the axis is rotating counterclockwise. And negative angle will take when axis is rotating clockwise. Okay. So this one, this will become your traction. Now, here I should take the also 5 negative, but I will tell you later. Now you can do it with positive also. No problem. Just use the value. So now you have to tell me what is sigma and what is tau. Everybody has a calculator with you. You keep a calculator along with you when you come to this class. Now I can show you the hint if you are not able to solve. Similar way you will do. Anybody got the answer? Or I give it as a homework.
Homework, sir.
Okay.
So 1.25.
1.25. Right. Sigma is 1.25. It's basically 5 cos square 60. That will become. And tau will be, this will be 5. Oh, sorry. Still not so good with this. Wait. So this one will be 5 cos square minus 60 degree, and this one will be minus 5 cos minus 60 and sine minus 60. Okay. This should be the answer you will get, and I think those who could not do it, you can do it in your home. The hint says I've already given. You have to first find out T dash on this plane, which is this, because it's the area which has increased now. Okay, and as a result, area become area by cos minus 60, and that's why that cos minus 60 will come up and will multiply.
Your voice is breaking.
My voice is breaking. Okay. Now it is okay. Maybe sometime it may happen. I'm not sure though.
No, sir.
Oh, all the time it is happening. Is
5
it happening?
minutes since.
Are you using a mobile device or laptop? Sometime in mobile it may happen. I'm trying to speak very slowly though. Okay. So what you are saying is you have to first calculate the traction on that plane, and that's also depend on the area of that plane. And then this is rotating, this was n and it is rotating minus 60 degrees this way. So you have to find out what is the unit normal vector of that n, and then you will get the result. Okay. So this is just one dimensional problem so far I have discussed. Just 1D problem. Just traction is in one plane. Now let us revisit the earlier figure. Okay. What was there? There is some force acting, and that force divided by the total area, we talked about traction. That was the initial definition I have given you about the traction. So force divided by area. Now let's assume this area got delta A. That means very small. Okay. So if the area becomes small, so applied force now on that area will also be small. See, this F1, F2, Fn, and this may be the body force meaning its own weight. These are the all forces which is acting on this body. So we are just cutting that body and showing you two phases. Now, as we know, according to Newton's third law, if I again combine these two, then there will be no force here because internal force is in the opposite direction. And so, see, that's why it is shown like this. You see, this is Tn and this is minus Tn. So if I again combine them, so this one will become 0. But if I cut it, so there will be this traction will remain in both the surface. Now, if I like to see a very small area, which is delta A, and if delta A tends to 0, then the actual definition of traction or the classical definition of traction become limit delta A tends to 0, del F by del A. That is where is the so in some form we also write this is same as df dA. Okay, this is also written like this. Basically, this is the actually definition of the traction. So the change of force in any surface with the change of area. Okay, that is what is the traction. So in other words, the force will be a function of area, definitely. So now you tell me, if this is the case, is this a true statement? Then does the stress exist at a point? The answer is yes, because it's basically ultimately a derivative of the force at a particular, area, or at a particular point in that area. So if I know that derivative, that is basically my traction, and from that traction I can make a normal direction and a shear direction. So actually stress exists at a point. If it doesn't, then we cannot move further with solid mechanics. But so far all the time, if somebody asks you what is stress, you always said it's the force by area. Now, if I would have asked you before, if it is force by area and if area tends to 0, what happened to that stress? You would have told me, sir, stress will become infinitely high because the area is going towards 0. So the stress will become extremely high. The idea is fine. It is the same thing, I think. But the question is, the force is also getting towards, a minimum value, so that their derivative exist, or a limit delta A tends to 0, del F by del A exists. That limit exists. And so that means it's a continuous function with the area. So force is a function of area when we basically have to calculate for traction or the stress. Okay. Now let me give you an example, or let me ask you a question. Let's say you are now at home and your mom asks you to basically nail a pin in the wall. Okay, so you have to nail a pin in the wall so that calendar or some photograph can be hanged. Okay, now you know solid mechanics, and let's say you are applying a force F, and in this case it's not an impulse force. Normally with hammer we give an impulse force. Let's assume we are giving a static force. Gradually we are giving the force F. Now this nail will go inside the wall because of the force or because of the stress? Or maybe the both. Do you get my question? You are applying a static force to nail a pin inside a wall. Now, is it entering into the wall due to the applied force or due to the stress?
Stress.
Due to the stress. Tell me why.
Sir, because
And why force cannot do it alone? Okay. Answer.
Because vaguely we have studied that when we nail a pin into a wall, due to the very less area at the bottom, it gets very easily pinned inside because it has very less area. So basically the traction will be very high.
Correct.
So
Exactly.
we can easily pin it.
Yeah.
So
Right. So what is happening is, if the pin is blunt in that top side where it is entering into the wall, then it will not go because the area is more. So It's basically force by area, which is stress, and that stress is exceeding the strength of that wall. So that's why it can go. So the wall has a strength and it will resist that stress until that strength. But as you have increased the force, and that's why this force is also important. As you have increased the force for a given area, then it exceeds that strength of the wall, and then that wall cracks and it goes inside. So actually, the stress at the tip, which is causing it to break or break the wall, it's not exactly the force. So this is how you should distinguish between the force, the traction, and the stress, which I will now explain it to you much more detail. So similarly, if I now say for the normal stress, it will be limit delta A tends to 0. Again, this force Fn, I have given a subscript n here, you can see. And this n is just to mention that it is the normal. And tau is our shear. So this is very easy to distinguish. And this S is basically in the shear direction, in any direction where your normal, your unit vector acts. So this is the classical definition of stress. So delta Fn is the force along the normal to the plane, and this is also along the normal to the shear. So is that clear so far? Okay. Now I go for 2D case. Now in 2D, what we have here is, let's say this is a plane, 2 plane now, okay, and the third plane is perpendicular to this screen. So we are ignoring that. It's just a plane. It's just on a plane. So this is a line. On that line, now we have 2 stresses are acting. One is normal to this plane, and another is shear along the plane. Similarly, in this plane, in the horizontal plane, there will be normal to that plane. Right now, do not see these values, just you see these. So this is the 2 stresses acting per plane. One is normal, one is shear. Now, if it is become 3D, I will come to that later. Then there will be one normal and 2 shear stress. And when in 2D, there will be one normal and one shear stress. Okay. Now the normal stress, I showed here the direction. You can see this is like a pulling that plane. So this is the direction of the tension we normally show. And if this, I would have given like this, then it would have shown as a compressing. So this is like compressing the plane, and this black one is pulling the plane. So pulling is tension and pushing is compression. Now, what is the difference? Difference is in solid mechanics, we use this as a positive, just sign convention. This will be positive and this will be negative. Okay, in solid mechanics, because you are also reading solid mechanics this time. That's why there will be a confusion, and just to take out that confusion, I'm telling you this. In solid mechanics, pulling force is tension, and pushing force is compression, which is negative. But in rock mechanics, it's just the reverse, because all of our stresses, most of our stresses, and not all, most of our stresses are compressive is nature, because it's the mother nature which is pushing below. And so or mostly if you just create some opening, then only some pulling happen. So that's why in rock mechanics, compressive will be positive and tension will be negative. So in this class, I will use this red one, and that will be positive. But in your solid mechanics class, they will say this one is negative. Do not confuse. Okay, that's why I am repeating this several times. Now comes the shear. Okay, so I have written somewhere the normal stress. This is sigma xx, sigma yy, or sigma zz. Sigma xx is just along the x-axis. Sigma yy is along the y-axis. So in our case, it will be like this, compression. Okay, so this is sigma yy, and this one will be sigma xx. So this is perpendicular to that plane. Now here plane are already given. A given plane is x and y having a 90 degree in between them. So this is the axis what we will have. And that's why you can see the subscript. This is along the x-axis. That's why this given xx. Many books will give you only 1x, but we will use 2x and 2y. Now for the shear stress, the definition is given here. You can see. The shear stress is this. How do we represent this 2 subscript? Okay. A shear stress acting perpendicular to x-axis and parallel to y-axis. Then this is the nomenclature. So this shows it is acting perpendicular to x-axis. You see this one, perpendicular to x-axis, and its direction is parallel to y-axis. That's why this is tau xy. So this one will be tau yx, because it's perpendicular to y-axis and parallel to x-axis. That's why it is written yx. Okay. So you remember that, the subscript meaning. Now I told you they are the tensor quantity. Now the tensor quantity meaning they have a magnitude. That means they have a value, either 5, 10, whatever MPa or Newton per millimeter square, whichever way you explain. They will have a direction, definitely. So these two say basically vector. Okay, this you know. Let me use the pen. You know, this we call vector quantity. Now, what is the tensor? There is a associated plane. Okay, the plane is associated with this. That means just by saying this is not enough. Okay, is associated with which plane I have to tell. Let me give you an example. Let's say I say sigma x-axis value is 5. Okay, and the value of this is also 5. Now, how do you distinguish? Okay, both of them have the same direction, the x direction. Both of them have the same value, let's say, the 5. Then how do I distinguish between these two? The distinguishing factor is this plane. This is acting on a plane which is parallel to y-axis. This is acting on a plane which is parallel to x-axis. So this is where it's become a tensor quantity. Okay, and since this stress is associated with a plane, we will not be able to apply all the properties of vector quantity. What are that? That a plus b equals to c, or a plus b equals to B plus A, okay, the vector. Or I can do the dot product, cross product, okay, very easily for a vector quantity. But for tensor, it is not so easy. Okay, we do, but directly we cannot do because the planes are different. You are seeing the, I hope you have understood the difference, that since they are acting in a two different plane, it will not be possible to apply the normal vector operations in a tensor quantity. Okay, we do, but we do it in a different way. So the sign convention of normal stress is given to you. Compressive is negative, tensile is positive. For solid mechanics, for rock mechanics is just the reverse, and that is what we will do. Now the question comes, what is the sign convention of shear stress? Let me tell you why I am saying this. If I go a little below, let me draw. Oh, wait. So I have drawn shear stress like this. Okay. Now let's say I'm drawing another one. Shear stress like this. Both the magnitude is 2. And by the way, I forgot to tell you, the tau yx, the magnitude will be same as tau xy. Magnitude will be same. Otherwise, you know, this particular point will be rotating, and we hardly see anywhere any ground is rotating. So that means these two shear stress are same. So if I take moment against any point, so these moments are balanced. You can see if I take this direction, this direction, so moment is balanced, so nothing is rotating. So now let's say these are the two configuration I have drawn for shear stress. This is 2 and this is 2. Now which one is positive and which one is negative? Now please hear me out very very carefully what I'm going to tell you right now regarding the positive and negative shear stress. Now first I'm giving you the definition of solid mechanics. Okay, if a shear stress is oriented towards a positive axis, okay, and the outward normal of that plane where that shear stress is acting, that is also acting towards a positive axis, then that shear stress will be positive, or vice versa. Now let me give you a example. Let's say this is the plane, and I join this side also. So this one will become shear stress like this, and the counter shear stress on this side will be that. Mind that this is the point. This is the stress acting at a point. Okay, so you will now see this shear stress. This is acting towards positive y-axis. So this is towards positive. Okay, positive y. And the outward normal of this plane is also towards positive x. Then this shear stress will be called as a positive shear stress by solid mechanics people. Similarly, you can see this one and the top one. Okay, I change the color, so then you will be able to see. So this one acting towards positive x, and its outward normal also of that plane also acting towards positive. So this shear stress is also positive. Now what about this one? This is towards negative, acting towards negative, and its outward normal also towards negative. So 2 negative negative is also positive. That means this configuration, what I have drawn here, is a positive shear stress. Okay, as far as solid mechanics is concerned. So in a solid mechanics, if they give you 2, you will write it positive 2 in the equation. But in rock mechanics is just the reverse. This will become negative configuration. So what I will ask you, just remember one configuration, that's it. So I'm giving you again, this is the point. The shear stress are acting like this. This one is positive value in solid mechanics. Okay, in solid mech, this is positive. In rock mech, it is positive. In rock mech, this is negative. So this configuration, if you remember, the other one is very easy. See, this one is just the reverse. See, this is this direction, this is this direction, this is this, and this is this. So it's just a reverse. Even if it is written 2, when you will use in the equation in solid mechanics, you will write it -2. Okay. Otherwise, your everything will be wrong. So you remember this configuration, then it's good enough. That if it looks like this, then it will be positive in solid mechanics, negative in rock mechanics. That's it. So any other will be opposite. Is that clear? I hope. The sign convention of the shear stress. Okay. You understood? Okay. Now I have another 5 minutes or so left. So let me give you a another thing about the shear stress. Actually, what is happening? Let's say I have, sorry. This is compressional normal stress in a point, okay, or let's say in an element. So what will happen is this one will become like this, right? Whatever the, depending on the stress applied, we are trying to change the size. So size is getting changed. Oops. Okay, so we are trying to change the size by doing this. Okay, by normal stress. So normal stress is changing the size. Now let's say again I have this and I have shear stress. Now what it is doing? This is changing it. Sorry. So it is changing it something like that. Okay, or reverse way. In this case, maybe it is something like that. Either way, it is trying to do. So this is this is what normal stress does. This is what shear stress does. Okay. So the normal stress changes the size. If you are pulling it, the size will increase. If you are pushing it, size will go down. And the shear stress is basically changing the shape. Now, when you are applying both together, so
Sir, please unmute.
I don't know how it is happening. Okay, can you hear now?
Yes, sir.
Okay, so if I now apply both together, so basically this is what actually happens in the field in a 2D format, but it's actually 3D. So if I apply this, so what it is trying to do, it is changing the shape as well as it may be sharing it also. So its shape can be in any direction. Now, when this kind of transformation happens, so we have to basically figure it out, which stress has done what. Okay. So how this one is transforming to this. Okay. And if we can figure it out, how it is doing this, we understood the solid mechanics or rock mechanics for that matter. Okay, how the stress is changing the size as well as shape of a particular element or the entire body or entire structure. Let's say you are living in a home. You have a pillar and tie beams. If you have seen the construction of a house or anything, they make some vertical pillars and there are some horizontal beams. So what are those? They are these load bearing units. Okay, and they undergo this shape and size changes. But we put enough strength. That's why we put rods inside and all this stuff and the cement in a proper mix. So that whatever the load comes, it will not be deformed that much. Now definitely if earthquake load comes, it cannot take that much. So if it deformed too much, so that it collapses. Okay. But in a static loading case, our game is to, from this shape, how it comes to this shape. So there is a relationship now with what we call, displacement. So that means something has caused the displacement. Okay. In your first year, you mostly used mechanics of rigid bodies, right? Although for beam, probably you have calculated the displacement, but all your force equilibrium in your static or moment equilibrium, the teacher has never said this much forces applied and how much was the displacement or we also call deformation. Okay. Okay, they have never told you that because we consider rigid body that not deformable bodies. Now we are coming to that the body will deform due to this load. So how does it deform? That we must know. So we must understand now also the displacement and the deformation. Okay. So I will stop here today, and the next class, what we will do, we'll find out the relationship between displacement and what we call the strain. First, I will give you the definition of strain. So far, you understood the definition of stress and traction. Then I will give you the definition of strain and displacement. Okay. Now, one thing remains, though. I think my Chamant and Gopi will try to know from you, and they will resolve the issue of Friday. So I have given them some option. Either we can shift it on Saturday or Friday afternoon, if you like. Let us see what will be your response. So please respond to their queries. They will send you a query, and please, all of you should respond because everybody 100% should agree when you move a date. Okay. So thank you.